Hi there. Welcome to my first attempt at doing lecture via YouTube. Please excuse any flubs or stuttering that occurs. This is a new experience for me, and when I get back, hopefully you can tell me how it went. Okay, so we are going to cover a little bit more of Newton's universal law of gravitation today. We're specifically going to focus on doing some example problems. First, let's summarize what we've covered so far. First of all, we learned a little bit about what Newton discovered about how the universe works. It appears that the gravitational between two forces can be expressed as gmm over r squared, where the magnitude of that force is proportional to the product of the two masses of the object in question, and then the square of the distance between them. And then the next thing we did, after looking at the force a little bit, we used the definition of work that we learned back in Physics 211 to integrate the force, and then we defined the universal gravitational energy as given in the equation here. Remember, U is the symbol we like to use for potential energy. Finally, what we did more on Wednesday is that we looked at the problem-solving strategies that we developed in Physics 211 and discovered that they work just fine for problems dealing with this new concept of Newton's law of universal gravitation. We also talked about some assumptions that we're making with Newton's theory of gravity. One of them is that gravity works the same everywhere. And one of the reasons we remembered Newton is Newton unified some very different natural phenomena. Today, if you ask a kid, why does an apple fall? Well, he or she will answer, because of gravity. And then if you ask the same kid, why does the moon go across the sky and orbit the Earth? They'd also answer, because of gravity. And those are two very different physical phenomena. An apple is something you can touch and eat. Meanwhile, the moon is this white orb or white glowing thing that moves across the sky. Who'd ever thunk that just a single phenomena, gravity, could explain both phenomena? And so we're going to assume that gravity indeed works not just for apples and moons and planets, but also for stars that explode and galaxies, which are collections of 500 billion suns. So let's try a sample problem with this. Let's try finding the mass of the Andromeda Galaxy. Okay, the Andromeda Galaxy is the sister galaxy to our galaxy. Our galaxy is called the Milky Way. And when you're looking at that object on the screen here, you're looking at a collection of 500 billion suns. All these suns have velocity vectors, and they orbit the center of mass of that galaxy, just like all the planets in our solar system orbit the center of mass of the solar system. Just in this case, we've got 500 billion suns and all their planets and moons and everything else thrown into that one kind of pretty picture we have right in front of us. Okay, let's try reading the problem and see if we can try to figure out what this problem is asking for and try to solve. Notice there's lots of words in here you might not recognize, but basically, using something called the Cepheid variable luminosity method, we can find out how far away the Andromeda Galaxy is. It's 2.51 million light years away. That means it takes 2.5 million years for a photon of light from that galaxy to get from there to here. The halo of Andromeda is 2.22 times 10 to the 5 light years from side to side. By halo, we're talking about the suns in the very furthest reaches of the galaxy. So the suns furthest away from the core seem to be 1.11 times 10 to the 5 light years from the core. So the radius is half of the number that's given there. And a star in the halo we can measure using something called the Doppler effect, which we'll get to later in the term. Has a speed of 0.07% the speed of light. Okay, using this information, we're going to try to figure out what the mass of this galaxy is. I'm going to have you do this together as groups, but before we do that, let me give you a little hint, a little foreshadowing of what we're going to do later. It turns out when you have a spherical collection of matter or a disc-shaped collection of matter, here we've got a disc-shaped collection of suns, if you're on the very outside of all these suns, the gravity you feel from the entire collection of suns is as if all that mass was concentrated at the center of mass of the object. So in this case, if you're an outermost sun, you feel a gravitational attraction equivalent to as if all the mass in that galaxy were concentrated at the center. There's something called the spherical shell theorem that we will cover later in class. It'll prove this to you. Right now, let's just accept it. Okay, so with your neighbors, you're going to try to find the mass of this galaxy. And of course, there's a way to go about solving a problem that has been successful for us in Physics 211, so let's continue to try to use it. With your neighbors, try to do the standard drawing of a picture and drawing of free body diagrams and using and deriving equations that we've been doing to see if you can try to figure out what the mass of this galaxy is. And what I'd like you to do is I'd like you to pause this and work on this with your neighbors for about 7 minutes. So go ahead and pause this now. Okay, so let's see if we can work on this now as a group. So hopefully the first thing you did, as you should always do, is you drew a picture. And in this case, we might want to first try to look at it from a side view. That's kind of the way the picture was oriented for us. And for a side view, sorry about my drawing here, I'm drawing at a strange angle. We had a whole bunch of suns that were orbiting an axis that goes through the center of mass of this disk-shaped galaxy. So if we had a sun here on the edge, it goes around the core, just kind of like how a planet in the solar system goes around our sun, or at least the center of mass of the solar system. Let's try drawing a top view of what goes on. That might actually give us more to work with. Again, with the top view, the single sun here on the right is orbiting the center of mass of the galaxy as a whole. So our top view would look something like that. In our picture, we should try to include information that was given to us. We were given this distance right here. Let's call it d for diameter of the galaxy. And we were also given the velocity of the speed or velocity of the outermost suns as they orbit the galaxy as a whole. Okay, and maybe on our picture we should write down the numbers that were given to us. We were given that d equals 2.51 million light years. By the way, the Andromeda Galaxy is the closest big galaxy to ours, so even the closest galaxy is 2 million years of light travel away from us, just staggering distances. We were also given that the speed was, sorry, I have to go back and take a look at that. What was it? It was 0.07% the speed of light, or in other words, it was 0.0007 c. We're going to have to convert all these numbers into SI units, so in meters, kilograms, and seconds in order to solve this, but right now let's just keep that like that. The next step is, of course, let's call this step 2, is draw a free body diagram. And as we draw our free body diagram, we're going to represent the entire galaxy as a dot, like we, we're going to draw a free body diagram for the sun that's orbiting the galaxy. So for this outermost sun, we're going to represent it as a dot. It's always a good idea to put in a coordinate system, although that's not too necessary in this case. And the only force acting on that sun is the force due to gravity from all the mass in that galaxy. Let's label that F of G. And our free body diagram is not done yet. We always need to put in the net force as well. And the net force is going to point inward, and it's going to be equal to the centripetal force. Because that sun is moving in a circle, we know that the sum of the forces have to add up to mv squared over r, which is the centripetal force. So in other words, as we try to derive the equations, we're going to get that F of gravity is going to equal the centripetal force, or gmm over r squared is going to equal mv squared over r. The little m is going to be the mass of our star. The big M is going to be the mass of our galaxy. Over here, it is the star that is moving, so on the right-hand side, it is also a mass of the star. And we notice that the mass of that star that we're looking at doesn't matter because it cancels out as it's on both sides of the equation. We're now going to try to solve this equation for V. And as we solve this equation for V, we end up, oh sorry, we're not solving for V, we're solving for the mass of the galaxy, as that's what we're trying to find. We're going to get that the mass of the galaxy is going to equal the speed of that sun squared r over big G. So we've solved the problem symbolically. You should always check your units. In this case, the units will end up working out. You should convince yourself that, of course. And then we start plugging and chugging numbers. And when we do that, we end up getting, or rather I end up getting, a mass of the galaxy equal to 1.38 times 10 to the 42 kilograms. You of course shouldn't take me at my word. You should attempt working this out yourself. And you could bet, because we're dealing with universal gravity, that in this next exam there's going to be really large numbers you have to multiply. So make sure you get good at those cheap calculators. So I get a mass of this galaxy being around 10 to the 42 kilograms. That's a really large number, even compared to other large numbers, such as the national debt. What is interesting, when we look back at this picture, people who have gone through and counted all the visible suns as well as much of the invisible matter